say that number out loud? What's the mass of sodium iodide? All right. Do you see it? 1.270 going back and forth. 1.270, 1.269. All right. Very good. So these are the initial measurement. To those initial measurements, I want to add small amount of water. So I'll be choosing the smallest beaker. So a small beaker. So I want to add roughly 10 milliliter of water. So these are rough measurements. And then here's my calcium chloride dihydrate. All right. So if there's any leftover of that measurement, okay. So I guess it will be maybe 1 or 2 grains. Okay. So I guess the best of the best as far as delivering any amount, since the amount of water is immaterial. So I'm going to just rinse it because that paper, that weighing paper, is slippery, would allow rinsing. See what happened? So I've rinsed any possible tiny particles of that measure. Okay. So notice it should dissolve quickly. So I'm going to let it sit for a while. If it doesn't dissolve, I'm going to just force it to dissolve. So to another smaller beaker. So I'll be choosing 20 milliliter flask, 125. So it's a 100 milliliter beaker. I want to add roughly 30 to 40 milliliter of water. It doesn't matter the amount, once again. So I guess any measurements, I can measure straight from these lousy measurements, lousy markings. I can use them because the amount of water is immaterial, but here's the sum of it, just to make sure that we fall in some direction. But the amount of water for both is not critical. It becomes an issue once we want to evaporate all that water. So a massive amount of water, a liter, for example, sizable for those tiny quantities, but they're going to suffer on the way out when trying to evaporate all that water. So here's my 30 milliliter, roughly. So I'll stick around to the low range as good as possible. The next, I want to dissolve. So I'll dissolve 1.25. Now once again, so here's the technique. So since the weighing paper will allow to slip or to have all these water molecules to slide without any stopping, so and I would not add any material other than whatever those particles that would remain inside the weighing paper. And this is a good technique. So once again, these should dissolve readily. That solid, I guess, it doesn't have to be dissolved. It should dissolve. Right now it looks cloudy, like a disaster, but eventually it should dissolve. The same as the other one. So the other one kind of cleared out a bit. I don't see any particles. Do you see it? So that's the first solution, the calcium chloride. The sodium iodide may take a little few minutes. So now I'm trying to shake it with the help to stir with the help of the stirring rod. Any particles that would be clung or hung on that stirring rod has to be removed. I can rinse them down since the amount of material, the amount of water is not critical. I'll notice how that solution cleared a bit. I want to dissolve them completely in such a way as when I add them, I want to quickly add them together and the reaction is swift. So add them together without dissolving all these particles might create sort of structures or complex in such a way as they're possibly hiding something inside not reacted or something that will be reacting. Make sure all these solutes completely disappeared and dissolve in their water. Okay, so if you can observe it, so make the observation. So now the solution and particles remaining. One particle. So there. All right. So I guess it's gone. Great. So now I want to rinse that stirring rod. So I'm using just room temperature for now. Second part, I could leave it. I could have left it. Not a big deal. So the second part, just show you separately. I want to mix the calcium chloride dihydrate with the sodium iodate. Okay, so the mixture is going to generate some calcium. So notice the mixture. So when I mix them, okay, so I end up with that cloudy solution. So I want that beaker. So rinse in that beaker, the last grain of the very last particle of that calcium chloride dihydrate. So I'm going to tilt it to almost 15 to 20 degrees, and rinsing it all around. So I'm going to rinse the internal walls all around. So that delivered the last of the last. So keeping it angled at 15 degrees and just rinse the internal with that dry water, and all the particles are delivered. All right, so for this one, it's going to take a while. Okay, so what I have in here basically is a reaction between the iodate and the calcium iodate is going to crystallize. Okay, but that crystal is going to somehow materialize. So as you notice, there's some kind of a white powder or crystals are start to form. So I can just shake this solution, agitate a little bit. And then I'll be collecting it using gravity filtration. So I'm going to let it stand for 10 minutes. It's going to take a while. So I'm going to leave it there for 10 minutes. We'll come back to it. So we've done the preparation of calcium iodate. Calcium iodate will crystallize, will be collected in filter paper. So let's go back to our setup. So in here, So following these pages. So we're going to prepare, which is coming up very soon. So I want to crystallize all these possible crystals of calcium iodide. I want to collect them inside a filter paper. So the setup to gravity filtration, as a reminder, is the following. Right, so let me show the setup in the winders. So here's the setup of filtering technique. So we call that gravity filtration. So what I have is as simple as a collecting bottle, an iron stand, an iron ring, and I've added that little setup because that iron basically is sizable based on the size of the funnel. It would not fit. So I've added some kind of a hook or sort of a base for it to hang. So I'm using that clear triangle. The funnel has to be clean, and the glassware to collect the filtrate. The water is always, or the liquidy material to be collected upon filtration is called filtrate. Typically, we waste it. We're not interested of the filtrate that would be generated because you're going to back up whatever they're trying to collect in here with rinsing solution, rinsing water, rinsing some acetone, rinsing of other materials. So the rinse and whatever they collect in here, the liquid, basically, we're not interested in. Okay, so we're going to shove it on side. Sometimes you go after it. So it depends. For today, we're going to collect the crystals inside the filter paper. So let's weigh out a filter paper. So these are generic filter paper. They call number 1 filter paper. So I guess a filter paper before you snug it inside the funnel. So first you have to fold it once. I'm not using blocks, actually. So I'm folding it once. Then I want to fold it a second time and create that boat. Open on one side. Okay. And then you stuff it inside the funnel. It would not sit, as you notice. No matter how much I'm trying to hold on to it, it would not sit. Okay, it keeps on popping up. So I want to somehow stabilize it and just wet it a little bit. So I'm going to just wet the surface a little bit. Eventually, it will finalize itself to be sitting. So it will sit eventually. So make sure all the sides are wet. So this is what I mean. So the filter paper is all wet and it is seated. So I'm ready to go as far as the filtration. So we need to somehow, as far as those crystals, so a few words about those crystals. So all I'm going to do, the next step is to take those crystals and filter them using the filter paper. I want to collect them inside the filter paper. Sometimes, depending on the crystals, sometimes they crystallize and collect themselves quickly. Sometimes it takes a while. For those crystals, the longer you wait, the better. I guess you're going to wait forever until you collect the last crystal to be collected in that solution. The crystals that I'm collecting basically is calcium iodide. But then it will take a while. I'm not going to wait. So I'm going to give it like a chance of 10 minutes on its own to figure out to collect itself on its own. Sometimes crystallization along that line does not materialize. Okay. If it doesn't, then you have to just come in and just knock. Okay, so give it a little tap physically. So those crystals sometimes may enter what's known as a deep sleep, and they tend to forget what to do at a certain temperature, at a certain environment, and they forgot to crystallize. So I want to somehow give them sort of a knock or agitation. So So either we agitate the internal glassware using a glass rod, or we can add maybe a drop or two or some foreign solution of their own. Maybe a tiny grain of, let's say, calcium chloride, or maybe a tiny grain of sodium iodide, maybe their solution, maybe go on the outside and knock on them, knock, knock. Yeah, as similar as physical tapping on that glassware. They'll tend to somehow awaken, start to crystallize. And that crystallization will take a while. So if you leave it until tomorrow, definitely collect the maximum number of them. But I'm going to just agitate them. I'm going to push them physically to form the big number of them by having an ice water. So I'll be right back to get an ice water. Okay, I'm going to time myself for 10 minutes for that crystal to somehow collect the best amount. And I'll be right back for the ice water. So I came back with the following. So I was cooling down the eye water. You got some DI water cooling down. So it's not getting inside the freezer. So that water has to be like a really, really cold, frozen. Can you hear it? So that's a frozen, almost frozen water. So I want to use that very low temperature water as a rinsing water eventually. As far as the beaker, okay, so I guess, let me see. So here's some beaker. Let me put this on the side for a second. I just want to collect a small amount of ice and just make a little slurry. So just add in some water, maybe cold water. Leave it cold on top of the ice. So as far as the filter paper, okay, so one thing we need to do about that filter paper, they all look alike, they all similar, hopefully. So I'm going to grab a second filter paper and mess it. Okay, so I'm on to page 79. Page 39, which is I'm waiting for that process of those crystals to crystallize, and I'll be collecting using cold water. So I'll be measuring the mass of one filter paper, and that could be recorded. So that's the filter paper, the same brand of filter paper snuck in inside the funnel. That's the mass of one filter paper. Perfect, 1 gram. The filter paper has 1 gram, the mass of each. Record the mass of filter paper, which is 1 gram. So they also recommend to measure the mass of some watch glass. So I don't have watch glass, but I have evaporating dish. So I can mass the evaporating dish like this. Okay, so I'll be collecting the solid, the crystals after filtering, and then I want to put it inside that dish. I'm going to wait on it so it dries. So the idea basically is to collect those crystals, dry them while being inside the lab. We typically return back to it. Okay, so a setup for the actual lab on Rio Hondo College basically is to collect the crystals and store them in your drawer and come back to them the next year to be able to collect the mass. So tonight, I guess the best of the best way of doing it basically is to collect the crystals, and then we'll come back. Well, I can give you the weight after drying because I need to dry them very good. Not drying the crystals, eventually the mass will be mistakenly as mass of the dried crystals will be higher. Typically, will be much more higher because the wetness. So I guess to that part, what I'm trying to say, I'm going to leave it empty. The part that would say evaporating dish, so I'm going to leave it empty because the uh, the intention and the idea basically, I'm going to leave it time. I'll give it to you back. Okay, so once the filter paper is completely dry, so I'm going to give it to you back. The reason because sometimes the watch glass or the dish somehow is needed as with just in case of an accident and so many samples seated next to each other, there's a chance, a possibility of some of your crystals will ooze out from that filter paper onto your neighbors or some other samples and contaminate all the samples, or some samples would not be accurate as far as the mass. So we end up losing data. So we need to collect all these possible mishaps and possibility of the crystals oozing out from that filter paper using some sort of a dish to collect them. That's the idea of it. But I'm going to skip it. So how we're doing time-wise? So we pass about I believe 6.5 minutes. So for another 2 minutes. So so easy crystals for me. So those are, let's see, because I'm adding ice where eventually they solidify one more time, but I want to keep them separated. So I guess we're ready as far as to finalize that crystallization. So crystallization, I'll be collecting more and more of them because I'm following the property of calcium iodate. Calcium iodate has a unique property. At a cold temperature, I'll be able to collect a good number of the crystals. They would not dissolve, so their solubility goes down with a lower temperature. So he's increase my chance of collecting more of them. So now definitely, so I want to rinse the a little more. Great. So now I want to rinse whatever those in here, but I'll be careful. So now, from now on, all the materials, all the water that will go in, rinse in, or whatever that has to be, as far as the solution, has to be cold water. Because the room temperature and hotter water, eventually, those crystals gonna melt back to being invisible. So that's the way to keep them. So we kept them outside to try to crystallize on their own, and they did for quite a bit. But then I want to also keep them for a full. I'm going to give them a chance, which is the best chance to solidify at very cold, low temperature. So let's continue the calculation. Okay. Let's go back. I'll be back to these pages. So flip pages on to page 82. So turn on to page 82. Right. So let's attempt writing the reaction between calcium chloride dihydrate and sodium iodide. So calcium. And then dihydrate. So that reacts with sodium iodide. So these are aqueous. And they're going to form solid. Or recrystallized solid at lower temperature. But notice, I'm collecting salt, but that solid would not be fully collected unless I cool down the temperature. So I'm going to use lower temperature, so it's not heat. I'm going to cool it. So by cooling. And then I'll be collecting the calcium iodide. So I'm just swapping around between the iodide and the chloride. And then to sodium chloride.
Why are you multiplying by water?
Oh,
Yeah.
actually, that dot represents that water molecules are attached to the thing.
Went over this before, so it's not multiplying. Where is my? All right. So was that clear? So it's aqueous. You're gonna stay in solution, clear. Okay, sodium chloride will dissolve. This one will give you like a sort of a hint of something in the solution, like cloudy, but then it's a little bit heavy. Calcium iodide is heavy. The real mass is from the iodine ion. The iodine basically is very heavy, mass-wise, followed by O3. That will add up so much of weight. Calcium is not as bad. I mean, as far as chloride twice. So that's a real mass. Okay, and you see that real mass quickly settle. Okay, so that flour would settle because it's a little bit heavy. Okay, but then I want to build more of it. Okay, so this is sort of a, let's write down this is solid and to be collected. Okay, so after that, solid being generated and collected. So looking at that balance reaction. So let's do some calculation. Alright, so as far as that reaction, which is balanced, I'm looking at the mass of calcium chloride dihydrate. Okay, so we think the mass been used. So what was that mass that we used? What was the mass? How much of calcium chloride dihydrate that we used? What's the mass of the sample?
0.548 grams.
0.548 grams. And how much of sodium iodate?
1.269
grams. All right. So I want to see exactly if I start with 0.548 grams of calcium chloride dihydrate. How many moles of calcium iodate are possibly to be generated? And the same goes if I start with 1.269 grams of sodium iodate and all of it reacted and consumed into making the product calcium iodate. Well, how many moles are there? Okay. So once again, so I'll be using, so they're trying to break down the calculation for us. So here they give the calculation. You start with the mass, then the molar mass, and then how many moles. So using the molar mass, which is 147. So the molar mass of calcium chloride dihydrate is 147.01, 0.02 grams per mole. So this is to be run on the second line. Okay, the molar mass. All right, so you follow me? So just follow me. So write down the mass of calcium chloride sample, which is 0.548 grams. The molar mass is 147.02 grams per mole. Now, how many moles? So how do you figure out how many moles? So divide the mass of calcium chloride dihydrate by its molar mass. So that's the mass of calcium chloride dihydrate divided by the molar mass, which is 147.02 grams per mole. And that number is what?
I think it's 0.0037.
0.0037.
But I don't know what to do with that 2H2O. I don't know if I factor that into it. I didn't.
What do you mean? So just simple division, dividing the 0.548 grams by 147.02. Just dividing these two numbers.
Okay.
This is just the grams of that compound. Okay, so that's the grammage amount of that compound, calcium chloride dihydrate. That's the mass of it. So divide that mass by 147.02, and this is what you got, right?
Yes.
So these are the moles of the calcium chloride dihydrate. So you follow me with these values. So that's the third line. Remember those lines? So the third line. So the third line, three top lines. The third line is the moles of calcium fluoride based on that measured amount. So we end up having 0.0037 moles of calcium fluoride dihydrate. Now, notice the formula of calcium fluoride dihydrate. So dihydrate, for every 1 mole of it, how many moles of water? 2. How many moles of calcium chloride? 1. Will be the same. So if you start with that 0.0037 moles of the hydrate, well, how many dry out anhydrous calcium chloride? Should be the same. Agree? Because based on that formula, a mole of that hydrate has in it 1 mole of anhydrous, 2 moles of water. So if you start with 0.0037 moles of the hydrate substance, or how many moles of the anhydrous, will be the same. It's a mole to mole, right? The mole ratio is 1 mole of calcium chloride, and there'll be 2 moles of water in every 1 mole of calcium chloride dihydrate. So the fourth line that will ask for the moles of calcium chloride will be the same. So write down the same. So it will be the same. So the next line, the fourth line, will say exactly the same, which is 0.0037 moles of calcium chloride. Agree? So that's your fourth line. All right. The next part, want to measure based on the initial measurements of sodium iodide. Okay, so we're going to start on the measurement of sodium iodide. Okay, so here's the mass of it. So that to be ran 1, 2, 3, 4, 5. On the fifth line, next to the adjacent the mass of sodium iodide, so write down 1.269 grams. How many moles are these? So I want to divide 1.269 grams of sodium iodide by the mole mass, and the mole mass is 197. What was the mole mass? 1.8. Agree? Grams per mole. Alright, so I'm going to divide that mass of sodium iodide by its molar mass, 197.8 grams per mole. Okay, so can you give me that value?
Mm.
0.0064.
0.0064. So these are moles of sodium iodide. All right, so the next part, so to cover this page fully together, as in group, we're all doing it in class. The last line, so this is line number 7, the moles of these sodium iodide is 0.0064 moles. All right, so now flip to the second page, move on to page 83. So this has been cool, and I guess the best of the best as far as collecting those crystals is what we have right now. All right, so we'll come back to it. All right, let's collect them first. It's gonna take a while for them to filter out, and it's a gravity filtration, very slow technique, but then it minimizes the losses. Okay, so let's hold on for 1 second. Let's do that maneuver and start filtering, and then we'll come back to those calculations. So now the filtering will start this way. Since the media that I've collected all these crystals is freezing cold, want to maintain the same media, which is freezing cold temperatures, while I'm trying to filter them or rinsing them. So at no time you want to come in with regular tap water, regular DI water, room temperature, and trying to rinse them or do anything, they're going to dissolve. You're going to lose them. Okay? So to maintain them and have them all together with a large quantity as possible. So I want to somehow use very cold rinsing water, very cold glass. So I guess one technique, so maintain that glass to be cold, so the environment should not be subject to heat. All right. So I'm going to start by discarding. Can you see? So I'm going to first start with that cleared out solution. Trying to get rid of it first. So we go back to the same cold environment. So the reason that I want to get rid of that clear solution, so typically what I've seen, or what sometimes they're recommended to do, is to mess up the whole thing, to mix up the crystals once again. Once you have precipitated crystals, you shake that solution quickly, and then trying to pour it down. That technique versus the technique which is the clear out. We're going to decant. We call that decanting the clear solution, meaning get rid of that clear solution first before you come into the scooping down the solid. Leave the solid on the last part of that solid descending onto that filter paper. Because filter paper, so I don't have a magnifier, good enough, but that filter paper has holes, has microboles, like very, very tiny microboles. The size of them depending on the manufacturer and the brand of that filter paper. But typically, they'll tend to be blocked a little bit or somehow like sort of covered, and this allowing liquid water to filter through, go through, the minute you add solid. So if your solution is cloudy, especially those heavy suspension and what are the property of the chemicals and viscosity of it, eventually might slow down the process of filtering. Because these micropores eventually will be busy with those particles, gigantic particles, trying to somehow to retain or not to go through. They should not go through eventually. But then while seated, they're going to block plenty of those millions of these micropores to the point of maybe slowing down the traffic of the water. So the best of the best as far as the filtering, let's get rid of the clear solution first, because they have the least number of particles that will slow down the traffic. Make sense? So the same by analogy, let's say you got 18-wheelers, maybe a few 18-wheelers, and you want to let them drive ahead of traffic. They tend to block the traffic versus maybe tiny motorcycles or like sport cars or some kind of tiny vehicles. Let them go first. Okay, then you allow the 18-wheelers to follow. Okay, they'll tend to go with traffic much better. You'll be collecting all these heavy objects later much sooner versus the other way around. So do not mix them. Don't mix them and then start to filter. Filter that, decant that clear solution first. All right, so just about there. Okay, so the next part I want to scoop down. So here's my technique. So I want to somehow pour it down. So sometimes if there's no spout for that beaker, there is. So every beaker has a little spout for the liquid to go through. So if there's none, you create that guidance, which is sort of a glass where the guide the liquid to go in to a particular direction. Okay, so I'll wait a little bit. So they tend to clear, so notice how that filtrate is collecting very fast. All right, so this is going to be collecting. Okay, and eventually after I collect all these solid, I want to rinse them. So it'll take a while. So I'm going to just pause for a second. We'll come back to it. Now let's continue and finish up our calculation. All right, so how many? Okay, so now on page 83. Okay, top of page 83. So assuming calcium chloride, all of it reacted, meaning it is the limited reagent. So you got reagent A, reagent B. Reagent A is fully consumed, fully converted into product. Okay, let's assume that reagent A is fully being consumed and fully converted into product. It means how many? What's the moles of calcium iodide would be forming if the whole amount of the moles of the calcium chloride dihydrate fully being consumed. So the meaning of that limited reagent, all of it is gone. All of it is being reacted. Okay. Well, how many moles of calcium chloride do we have? All right. So we have that many moles of calcium chloride. Assuming all that calcium chloride is gone into forming the product, calcium iodide. Okay. So how many moles of calcium iodide if the whole amount of calcium chloride is gone into a product? Well, look at that balance reaction. For every 1 mole of calcium chloride that we have, we're going to be generating 1 mole of calcium iodide. Agree? So it's a multimole. So thereby, so you can use that mole ratio, which is a multimole. So you can start from here and then apply that multimole ratio, which is convert that to a mole of calcium iodide. Mole ratio is one mole of calcium iodide from that balance reaction is forming and you can add that dot to a hydrate divided by a mole of 1 mole of calcium chloride dihydrate. So multimole. Okay, eventually that number is going to be none other than this value. So that number is the moles of that reacting calcium chloride dihydrate. It is the same as the moles of calcium chloride, the same as the moles of calcium iodide forming. Okay, if all of it to be reacting, it means it is the limited reagent. Limited reagent, it is the reagent that would be limited reaction from fully reacting the other completely react with the other, but the reagent itself, the limited reagent itself, is fully being reacted. Okay, so the idea of that limited reagent basically is to limit the other component not to fully react, but guarantee itself to fully react. Okay, so how many moles of calcium iodide? So write down that number. Would be the same, but use that formula first, which is convert that moles of calcium chloride dihydrate into moles of calcium iodide. Alright. Now, if all the moles of the sodium iodide are fully reacted, well, how many moles of calcium iodide? So be careful with that mole ratio, because the next time around, I want to start using the sodium iodide. When I go left to right, I note the coefficient, which is 2 moles of sodium iodide is capable to form a mole of calcium iodide. Okay, so I'm going to note that one. So it means if you start with that moles of sodium iodide, so how do you convert this to moles of calcium iodide? So I have 1 mole of making calcium iodide well, based on those mole coefficient, the mole ratio between them is, it took 2 moles. Agree? one mole formed. It took 2 moles of sodium iodide. So sodium iodide. And what's that number? So take that number divided by 2.
Oh, let's see. It would be a 0.0032 moles.
Moles, very good. So that's the calcium iodide.
Oh yeah. So from what I'm seeing right here is that I would use the coefficients in the balanced equation to do the mole to mole conversions.
Exactly. Yeah. Exactly. So those coefficients are critical for us. So before we start on those calculations, so make sure the reaction is balanced first. So while talking, I guess we're just about. So now, so he's the last of the last material. So now I'm allowed to shake it and mix it, which is fine. But I'll be careful with all these grains. So I want to collect all these grains to the last grain of it, to the last mark, one at a time. So just be careful. So in here, so I'm going to just angle it. So I show that part. So I'll be using the maneuver. So I want to angle it in this way. And I want to physically start dragging them physically. So the best way of having all these solid physically sifted down. I'm going to keep the angle like that. So now I got I'm going to go back to my ice water. So first I want to get rid of that. So I want to rinse that. So I want to rinse rubber policeman. I rinse it, just make sure no molecules, no chemicals are still attached to it. So I rinse it down with cold water. So that water in here has some ice. So this is done. And then I'm going to go back to that beaker. So tilt it at around 15 degrees, 20 degrees, and give it a rinse. I'm going to rinse it all around. So all that material has to be rinsed, and I did. So where you see that fog on the outside because the cold environment or the cold ice, but the inside are completely rinsed. Just make sure, so I'll get a second rinse. While rinsing, do not tilt it backward. Don't tilt it backward, you're going to be rinsing it many times. And you're still going to come up with a deficit. You're still going to have some locked in or molecules that are stubborn enough to stay behind and hung on the wall of that beaker. So always going to tilt it this way at 15 degrees angle, and you always rinse it in that position all the time, all day long, which will take a few seconds. Okay, so that's the last of the last rinse. And it should be done. So here's the third time I'm rinsing it. So what's left in that funnel basically is the supposedly calcium iodide. All right, so back to our measurements, back to those measurements. So up on top, I've collected based on their proposed limiter reagent. If the calcium chloride happens to be a limiter reagent, let me put this on. So they're asking us for it first. If calcium chloride happens to be a limiter reagent, for how many moles of calcium iodide? Okay, So we concluded that has to be 1-to-1. So it has to be 0.0037 moles of calcium iodide. If, on the other hand, sodium iodide is the limiter, but it's going to give us, if that is the limiter, all of it is gone and consumed, well, what's the amount of, how many moles of product of calcium iodide? So our calculation says 0.0032. Which one seems to be the smaller of the two?
Calcium iodide.
Calcium iodide. Okay, so the limiter in this case between these two measurements. So calcium iodide in our case for this reaction, based on the initial measurement, happens to be the limiter. It turns out to be the limiter 1.269 grams. It doesn't have enough of material to fully consume 0.548 grams of calcium chloride. So some portion of that grammage amount of calcium chloride is going to remain behind unreacted, which is fine. But it's going to remain in the liquid, in the filtrate. So what's going on with that filtrate? So I'm going to keep my product, which is the solidified calcium iodide inside the filter paper to be dried out. And what I'm rinsing and wasting and collecting down the filtrate is everything else, the in excess, which is calcium chloride dihydrate, all that water, which is unnecessary. So all that liquid that I'm collecting, basically, if there's any extra remaining unreacted, that calcium chloride is already been collected to be wasted.
Oh yeah. So in this case, the sodium iodide would be the limiting reagent?
Yeah.
Okay. Mm-hmm.
So that means so the limiting reagent is the sodium iodide. And the ones that to be considered in excess, extra, unreacted, would be calcium chloride.
Oh yeah. And should I not worry about writing the dihydrates?
Yeah, so you can just skip it because we're following the moles. Okay, the moles will ease up on instead of dragging the whole gigantic molecule on.
Yeah, we did find that the moles of the dihydrate is the same as the anhydrous solution.
Same as the hydrate, same as the unhydrate.
Yeah. Yeah. And so that would be a good reason to keep calcium chloride by itself.
Calcium chloride, yeah. So that water basically can easily be removed by simple heating. Okay, so we came across that one in experiment 5, if you remember. So we just simply heated the hydrate with no unknowns, and we easily remove those water molecules. But these water molecules are not the adsorbed water on the surface. These are embedded deep in within the crystal. And they can easily be removed because how much will it take to remove the water? What's the boiling temperature of water? 100. Remember? We struggle with generating like a very bleak, very, very minimum temperature on that Bunsen burner. Remember? We had an issue how to reduce it at below boiling temperature of water. So those water can easily be removed. Not a big deal. So using very, very faint heat, lower than 100 degrees. All right, so last part, basically I'll leave it to you. We're almost there as far as the calculation. Okay, so what remains on the last page, it waits for me to dry it, which would not be dried out and completely ready to be measured because I'm afraid there's still some work in it. But I'll do as best as I can to show you exactly how to accelerate the process of drying it. If you're forced to dry it on the spot, how would you do it? But then, to get the best of the best as far as the results, so I'm going to wait on it a little bit. So the next time around, I guess, or you wait for me until I give you that number, which is the mass of the filter paper plus the solid that remains. And that's all what you're waiting for. Once you get that, subtract away the mass of the filter paper, which is 1 gram. That would give you the mass of the calcium iodide. And from it, you can follow up the rest of the percent yield and the rest of the calculations.
Okay. Yeah.
So we can challenge that one as well. Okay, so it says, well, how many grams of calcium iodate? What do you think? How many grams of calcium iodate?
Let's see. Grams of calcium iodate. We would have to, let's see, do the.
Moles
Let's see.
based on the limiter.
Yeah.
So what's the quantity you anticipate? How many moles of that quantity of calcium iodate would be formed and generated based on the limiter?
Let's see. So let's see. We would start with the 0.0032 moles and convert that to grams.
So that's the limiter. That's the limiter. That's the limiter of the product calcium iodate. So start with that one and figure out what's the mass. Agree? So start with that number.
Yeah.
So 0.0032 grams. Moles of calcium iodate. Okay, so how do you turn it into grams? Well, a mole of it has what sort of molar mass? So 1 mole of calcium iodate has what sort of molar mass? Well, what is that molar mass of 147.02? Take away 2 water molecules, which is 36. So 147.02 minus 36. That's the molar mass of calcium. I'm sorry. No. We haven't gotten the molar mass of calcium iodate yet.
Okay.
What's the molar mass of calcium iodate?
Okay, molar mass. Let's see. Yeah, we just need to pull up a periodic table for those calculations.
All right. Can someone look it up and give me that molar mass of calcium iodate?
Oh yeah. No.
I got 389.88.
389.88 grams. Okay, so that's the mass of calcium iodate divided by per mole of calcium iodate. The mass of it is 389.88 grams. So multiply that number by 0.0032 moles. That will be your grammage amount of produced theoretically of calcium iodate. So multiply that number. 0.0032 times the molar mass of calcium iodate, and write down the answer down below. The grammage amount based on that limited moles of calcium iodate. Okay, what's that number?
$1.25 grams.
Of calcium iodate. Great. So far, we're rolling. So this is the grammage amount we expect, we anticipate. But typically, we always get less. We always get lower value. This is the anticipated. So if everything is perfect, life is not perfect. So if everything is perfect and no losses, means you'll be able to collect the following mass of calcium iodate, which is 1.25 grams. But let's see at the end. So this is how it looks. This is how it looks. Okay, so that white powder basically is your calcium iodate. But I need to rinse it, give it like a final rinse of very cold water. So I'm going down the water. So this is my way of going down the water. Got the ice packets, and I got my water going down constantly. So if you rinse it with a room temperature or slightly warm temperature, the result will be down the filtrate. You're gonna see your calcium iodate down there. So you won't be collecting the maximum number of them. Okay. So eventually we're after what's known as the yield, the amount of yield of that product. How much yield that can possibly be, how close we can get it to say 1.25. 1.5 is the maximum, the theoretical, the golden number to achieve, but we don't know. Okay. So in here, so when all that liquid is gone, all of it. So wait on it. So if you still have some liquid trying to rinse it, it's a bad idea to rinse it. But now I'm ready to rinse. So notice there's hardly any liquid remains. Now the rinse becomes effective. But if the water is still there, maybe a small amount, it doesn't matter. Once you have some water and you're trying to rinse it on top of it, you're not rinsing. You're just diluting. But now you expose the crystals. Now what you have is wet, sort of a slurish crystals. They're meant to be wet, so you want to go in between and rinse them, okay? But not their solution. And here's the cold water. I can add some ice just to make sure the water remains to be, because I want it to be as frozen as possible. I purposely added some ice. So now I want to rinse in. Okay, which is good enough. So it says rinse it for like 2 to 3 milliliter of very cold water. And I'm all set for the last stage. The last stage is to rinse it with acetone. And can you explain to me why it has to be so? So after that final rinse, once you expose the crystals upon that filtration, I give a rinse of maybe 1 shot or 2 shots of very tiny amounts of water, because they're going to come in direct contact with the crystals. So they're going to rinse them. Okay. Once you rinse them, I need to rinse them with acetone. Can you explain why it has to be rinsed with acetone? And here's my acetone. So why do I have to rinse with acetone? And the recommended amount somewhere between 5 to 7 milliliters.
Because acetone evaporates?
The acetone has a very, very good evaporation rate. Okay, what's that? Yeah, so once evaporate, it's going to pick on. So that jet of evaporation is going to pick along with it the water molecule. These water molecules. It'll take a while for it to evaporate, right? It comes in a lighter molecule, acetone comes in and trying to eject. So water molecules will be ejected along with it. So anyway, sort of an uplift in those water molecules quicker and accelerate them much quicker with that agent. Acetone becomes the backbone of drying or quicker drying. But we add in some organic definitely. So you'd rather dry it and completely get rid of it. So this is my 5 to 6, 7 somewhere. Okay, I don't want to waste much acetone. But we're gonna play the time. Okay, so I'm gonna give it a shot. So this is the outcome of those molecules. I'll show you exactly. So notice there's no more dribbling. So it means the solid exposed one more time. So you want to have that solid exposed one more time. Just solid flourish, but the molecules are exposed. They're not hidden behind the water level. So now I'm ready to add the acetone. So now another issue about the sign of whether or not we're doing it right. So here's the close-up. Can you see any cloudiness in that filtrate? We call this filtrate. You see any cloudiness?
No.
Okay, so it has to be clear. So indicating, so clear background, it means it is done perfectly. Any cloudy, it means some of these small particles are able to sneak out behind the filter paper and we're able to filter and claim to be inside the filtrate. You have to collect them and refilter. Yeah, if you got losses in here in that nature, if that turns cloudy, it means some particles found their way in from your crystal calcium iodide. You have to refilter that filtrate. So you can imagine filtering that filter will take a couple of hours. All right, so here's the first shot, and here's the second shot of trying to dry it. Okay, and we should be ready to go. So I'm ready to deliver it outside using. So I need a tweezer. So definitely, I was working with not so conscious about all these. Supposedly, with gloves, the gloves basically will minimize the measurements. Since all these measurements are like in range of, so notice 1.25 grams is anticipated, most likely going to collect maybe less than a gram, or sometimes far less. Who knows? Okay, so let's say collecting 0.2 grams, 0.5 grams, 0.3 grams, they're critical, definitely. So your the fingers, let's say, has oleic, linoleic acids, and some salts, and eventually, no matter how many times you wash them, it doesn't matter. We always have them on our hands. So eventually, touching any material is going to leave traces of them, your DNA, the traces of them. That small mass is somewhere in the thousands, maybe in the tenth of thousands. So 1/10,000 per 1 gram. So 1/10,000. That's how many grammage amount you can leave every time you touch some object. Okay. So touching them with their fingers eventually is going to leave that error. But don't keep touching them back and forth in the same spot. Eventually, you're going to create a massive amount of leftover from your fingers of their oleic acid, linoleic, or some salts. And that would add error, believe it or not. All right, so I'll be using it for the tweezer. So pretty much, so notice the dripping of that funnel kind of stopped, okay, because they entered the evaporation the other way around. So instead of dripping, because all that water stopped and the water is being uplifted, what if that water in between those crystals somehow, when it joined with the acetone somehow found them and blend them with or with it itself, and eventually and uplift itself with the water molecules. So it minimized the existence of the water molecules throughout, and the reason why that funnel sort of ceased to drop. There's no droplets. Can't dry out from here. There's nothing. All right, that's a sign. All right, so now what's left basically is to scoop it out. So here's my way to scoop it out. So first, I want to fold it as much as I can. So I'm going to fold it a couple times. And then I want to scoop it and leave it in here. Alright, so easy funnel. It needs to be clean. Everything's fine. No particles. Alright, so for that part, so it's all done and ready to go. What remains basically is to completely dry it. So typically, if we happen to be on Rio Hondo campus, we have a heating lamp, like a sizable heating lamp that delivers a good amount of wattage, and that wattage comes in and blasts the evaporating dish or the glass water for your sample to be dried. Small amount sample, which will dry quickly within 10 minutes, 10, 15 minutes. Sometimes if it's in half an hour, by the end of the class, we collect the mass and we'll walk away. Or sometimes we save them in a drawer and come back to them for the next meeting. Okay, so it depends. So I'm gonna hold on to them. Okay, so a remedy to this one, which is if you pop it in the oven, I would not pop it in my oven. So if there's a chemical oven, definitely not your cooking oven. So you can pop it in the oven for and just crank the temperature to in within 100 degrees, no more. You don't want to bake that sample. What you want is to deliver hot temperature hotter than the typical room temperature, less than 100, I guess, and then just wait with time. And within less than 1 hour, you end up with very dry, ready to be massed solid. So that's the last part that awaits for the whole process. So just to walk you through what we've done, so I'm going to wait on it until naturally with natural evaporation. I'll come back to it. So I'll send you an email that the mass of the calcium iodide is ready and the value of it. Fair? So this is what's left as far as the measurement. Okay. So the mass of the filter paper, which is already gone, that value 1 gram. The mass of the so skip that second one because we measure that one. The mass of calcium iodide filter paper. Okay. So I want to scoop out that iodide with the filter paper and mass it because I'm not punctured. There's no hole. So I was a little bit careful. Sometimes, like a scooping using a tweezer or some other tool, and sometimes you end up poking it and it creates sort of a little crack, or in a little crack, any little hole inside that filter paper, eventually your particle is going to sneak out. They become a little fluffy and very easy, like powdery and fluffy, and they can easily spread outside the filter paper. I didn't do that part. So all what I need basically is to scoop out that filter paper and mass it. Okay, which is coming up next. So I know the filter paper empty, the filter paper with my sample. The difference is the mass of sample, and then to figure out the percent yield is the mass of that sample on the last measurement, on the last line, divided by the theoretical mass that I've calculated on the page before. So the last page says I expect 1.25 grams of calcium iodide. So that goes down in denominator. In numerator is your last line, which would say the experimental calcium iodide. Okay, which is coming up not tonight, but then I'll work on it until it dries completely. I'll make you aware of the value. So you'll be able to complete and finish that part once you receive my measurement of calcium iodide, the experimental calcium iodide mass.
Okay.
Fair?
Oh, so I'm just wondering where should we check our email? So I'm just wondering, should I check in my Canvas shell to see your measurements for the?
Once I'll make it available,
okay.
So I guess I'll put it as an announcement and I'll send it as an email.
Okay, so you'd post it as an announcement and then you'd send it via email?
Yes. So I'll send you with different forms, different ways to let you know that it is ready for you. So you'll be able to quickly, because all the information, all the ideas are fresh, you'll be able to finish it quickly by tonight or maybe tomorrow.
Okay.
And you have like a simple post-lab question.
Okay.
And now we'll take care of the lab activity tonight.
Thank you.
We haven't left anything. So we've gone through all these pages. Okay. So any question at this point? Any question about what we've done?
Yeah, let's see. So, yeah, I think I'm just good here. Yeah.
So what's left for you guys to do is just to fill out the last page, waiting for my email that has in it the mass of calcium iodide, and should be all ready. Okay, so these are simply fairly explainable by themselves, but as you read along, you can fill them on your own by yourself. Okay, should be you should not get lost. Okay.
Yeah. Yeah. So in that case, I should just wait for your announcement of or email of the actual yields from the reaction.
Yeah, I would not. Yeah, so those are to be done by you. But I'll provide the mass of the filter paper with the sample. So I'll provide that one. And we know the mass of the filter paper empty, which is 1 gram. So we subtract the two, end up with the mass of calcium iodide.
Yeah. So the measurement you would be sending would be the mass of the calcium iodide with just the filter paper and not the and it would exclude the watch glass.
Yeah, because I didn't use it.
Yeah. Okay.
All right. Any other? And plus, answer that post-lab question. So now I'm trying to speed up as far as, because there's a few deadlines we're approaching. So so it took a while for me to catch on with the grading. While trying to give you the preview as soon as possible, so you'll be able to make a good judgment and sane decision about your progress in the lab. So as far as the lab, I have no fear about all of you. So you're progressing, and the progress basically is tremendously high. So I look the some other classes for other years. Basically, this class is very exciting. Some of you like in the upper straight A's as far as the performance. So keep it up. If you need help, if you're behind, okay, so trying to back me up. Whatever that low score, whatever that low grade that you got before, let's say, if I said, let's say that lab, you've given a value 1 or 2 or like a low number, work on it a little bit more. So talk to me, work on it a little bit more, see your chances. Well, sort of correct your mistakes. That's what I'm trying to say.
Oh yeah.
That happens to be just an error, but not something to redo the lab. So let's say 2 times 3 end up writing S5, which is, because I use my calculator. Sometimes I read your answers, read your numbers, don't make sense. Like simple calculation. Let's say 1,000 divided by 500 and end up to say 5 or some other number. Yes, things that are, I guess, as you're trying to rush through some goofy numbers appears in there, and now let's grab your result. So look them around, see exactly my notes. Okay, so I'm trying to help you out.
Oh yeah. I also just wanted to bring to your attention that I've been noticing that the grade for the nomenclature worksheet has been recorded as a 0.01 out of 10, and that just would bring a lot of our grades down by a large margin.
No. Okay, so if let's say if I add let's say a point, let's say 10 points, okay, to that nomenclature, okay, and the meant of, because the ones that are absentees are always give them 0.01, they don't show up. Once I click on it, you'll be in deficit regardless. Let's say you submit it, but I did not grade them, so you're always in the deficit. So whatever that value or percentage of performance will go down. You might not notice that one, but then that's the habit.
Oh yeah.
Because if the column is assigned a value, so I assigned initially that value because the fear of those are not showing or somehow either dropped or they continue popping up, but then they're not really submitting grades. So there's that automatic assignment to them, which is 0.1. Once that Canvas assign them automatically 0.01 upon the deadline. So with the deadline passes automatically, they're assigned 0.01. It means they did not submit. But what will do that as far as that technique, it'll lower everybody's submission or their values by up until I give them the grade out of 10.
Okay, so the 0.01, that would just be a temporary value, and then you would just eventually give a...
It's automatic for any non-submission. So if you owe me like a lab report or someone behind or did not submit for that particular lab, every time occurrence of that nature basically will get you 0.01. 0.01 is not 0. So I find it helpful as far as telling me, so I'm communicating with you and me, that I did not find your lab report. So you did not submit the lab report or I didn't find it.
Oh yeah, just so if it shows as a 0.01, like, just I think, so it probably means I could probably just try submitting it again or something?
Do you have any number of them with 0.01?
Yeah, I'm just seeing that with the nomenclature worksheet, and...
You submit it?
Let's see, I think, let me see if I'm just going to check my Canvas records. Okay. So, grades. Okay. Okay, so nomenclature workshop. Oh, yeah. Let's see, submitted. Yeah, okay. Open here, yep. Okay. Let's see. Okay. Let's see.
All right. Is there any other question to me?
Oh, yeah, I think that for some reason here, I'm just... Let's see, open with, okay, yeah, I'm just... Okay, yeah, I think that for some reason that... Yeah, I think that, for some reason I'm not really seeing any work for the nomenclature worksheet. That's probably why I'm seeing this 0.01 out of 10.
So I guess look it up. The file on the folder should be there because I put it through the announcement. Also in the folder for that experiment.
Yeah.
If you still have access to it, so print it out and just answer those questions. So resubmit.
Yeah. I think I already did do the questions, but just I think it could be that just when I tried to submit it, it just somehow just there are just some technical difficulties that might have gone wrong here.
Yeah, mine's the same. I can honestly recall turning it in, but it's not there.
You didn't find it? So try to resubmit.
Okay.
Yeah. So I could probably just try to maybe just resubmit. I'll just see if let's see, for some reason I'm just not able to resubmit it through Canvas.
Okay, so I guess let me just go back. So I need to give you a little bit more extension of submissions. So send me an email when these files are ready. So I'll give you another permission time to resubmit those files once they're ready.
Let's see. Yeah, I'm just trying to see if I ended up saving this actual PDF. Okay.
So let's say if you're let's say from your website on your own, let's say when you open the Canvas and you read my comments, because I showed back the grade materials. So when you open that one, are you able to submit attach a file or attach an answer? Like if you are you able to attach a file, that would also be considered as a second submission.
So let's see. So if I go here and let's see if I do see the add comment, and then there's the attach file option on the lower right.
Yeah, use that one. So it doesn't require to reopen the folder itself. You have access to give me like another submission internally.
Okay, yeah. So when I get the file ready, I could just place it under the attached file link.
And let me know. I'll look at it and give you back the grades.
Okay, thank you. Yeah, I'll just try to resubmit it right now, and I will see you next week, Professor.
Sure, no problem. Any other question?
Yeah.
If not, so you guys have a great night. I need to back you up with that information. So you guys have a great night. We'll see you next week.
I'll see you then.
Thank you.
Take care.
Oh, goodbye. Good night.